Good morning and welcome back, quantitative analysis students. We have just finished exam 2. We are officially at this point 2/3 of the way through our course. Sometime today or tomorrow, you'll see your grades posted in eCampus. As of late, basically everything that you've done up until now, it's kind of like another marking period. So you'll see your grades adjusted in WebAssign, on eCampus to include your WebAssign completions, your discussion posts, and your exam scores. Today, we're going to focus on Chapter 4.1.4.2, Inequalities in Linear Programming. First, we're going to talk about linear inequalities in two variables, and that is going to be our foundation. And then we're going to do some enrichment on that, and we're going to do an application of that. That application will be linear programming. Linear programming is a specific method that you can use to find out maximum and minimum values for certain specific business models. You'll see a couple of them today. One of them will have to do with the hours worked and the items produced. Another one will have to do with the farm and the different kinds of crops that you can grow based on how many acres you have and within constraints. And you'll find it to be actually an interesting application, at least I do. All right, so today we're going to start by talking about an old topic, something that you learned a while back, how to graph a linear inequality. So what is a linear inequality? Let's start with that. Well, an inequality is a statement, just like an equation is a statement. It's a true or false statement. However, for an equation, there's usually a finite, well, there's always a finite number, well, there's usually a finite number of solutions, usually one if you're in a linear equation. Those are the ones that you're used to seeing most of all. But when it comes to an inequality, there are infinitely many solutions if there's variable in there, because it's not about a quantity being equal to another quantity. It's about a quantity being greater than or maybe less than the other quantity. And because of that, your answers usually are a wide range of numbers that way. So before we do inequalities, let's just kind of take a glance at some very basic inequalities and discuss what they mean. We have, if you look here, 12 is greater than 9 is how you'd read that out loud. I'm just trying to refresh your memory. I know you've learned this before. 3 is less than or equal to 10. And then we have an inequality with a variable in it. 4x minus 7 is less than 20. Now, these inequalities are just statements. They can be true or false. Frankly, if you flip the sign around, it changes whether it's true or false is usually the way it goes. Unless it's an equals, it might have some values that it works for. But I just want to make sure we're clear with what an inequality is. It is a statement that compares two quantities in this way. And our symbols are there as well. I've heard little jokes about how you can pretend that the arrow looking thing looks kind of like an alligator's mouth and it's eating the bigger number. You know, I've heard that before. There's other jokes about how the point is smaller and the wide open end over there is larger. So the 12 gets the wide open end and then the 9 gets the tiny point that is the vertex of that angle. You could look at it in a couple different ways, but however you look at it, just please know when you see that first symbol, know it's greater than. When you see the next symbol, just know you have to, off the top of your head, kind of have that memorized, less than or equal to. Okay. Oh, one other thing I've heard that might help a little bit with remembering the less than sign, which is used in the last inequality, looks a little bit like the letter L. So L for less than is another way to remember it. Any way you can remember it, just make sure you have it committed to memory and you're familiar with those. All right, now let's talk about how you can use Desmos to graph an inequality. It's actually really a piece of cake. All you got to do is open up Desmos, put the inequality in there, and hit enter, and it just appears. It's that simple. Some things about these inequalities I want to mention. As you can see, we've graphed two inequalities on the same graph, and you're going to need to be able to graph many inequalities all on one graph when you're doing linear programming. It's a regular part of linear programming. So the good news is Desmos is very user-friendly. It makes it really, really easy for you to go in and put your inequalities in there, and it gives you nice, clear graphs right out the gate. They're color-coded, so as you can see, the blue one is the top one, and the green one is the bottom one there. And likewise, we have that important detail that if you are talking about a greater than situation, you have a dotted line. And if you have a greater than or equal to situation, you have a solid line. And if you look at the blue symbol is a greater than or equal to. And if you look at the blue graph, you'll see it has a boundary of a solid line. And that's because it is allowed to be equal to those values that are on that solid line because of the greater than or equal to. Likewise, for the green, you have a dotted line, and that's because it cannot be equal to 0, that quantity on the left for green. It has to be greater than 0. So there's something of an asymptotic situation going on where you will get as close as you can to something, but you never get there. And that's why it's a dotted line, meaning that all of the shading up to as far as you could get there Think about the idea of 0.9 and then 0.99 and then 0.999 and so on, how you're getting closer and closer to the number 1, but you'll never quite get there if you just keep on adding a 9 digit at the end each time. That's kind of the idea of what's going on there with the way that graph looks, okay? So in summary, you can use Desmos very easily to graph 2 inequalities at the same time. Desmos will also take into account which one is which using color coding, and it will also include the appropriate kind of shading and boundary line that we're used to from our algebra classes, which is for greater than or equal to, it's a solid line, and for just greater than or for just less than, of course, it would be a dotted line. Okay, so graphing an inequality should really be a cinch. For example, in chapter 4.1, our first example, please graph this inequality, go right to Desmos and put it in, and boom, there's your answer. It's a piece of cake. All right, so finding inequality graphs is so simple. You don't even have to think very hard. Once upon a time, you'd have to get a piece of graph paper and a ruler and a calculator and do some points and do some plotting and use a model equation and then do a test point. You might recall using that method when you were in high school where they teach that in Algebra 2. But remember, here in quantitative analysis, we want you to use those skills that you learned back in your secondary education and bring them to your higher education math classes with technology. So you already know how to do that. We're doing this now with technology. Okay, let's just do one more with regard to a system. So if we say graph the solution of a system, and we give you a system of inequalities, again, just go right to Desmos and pop them right in there. Just so that you know, actually, the solution to this is not really quite what you're looking at. I'd like to show you what the solution is right now by drawing it for you. Okay, I'm going to draw it in purple. It's going to be actually this part. Okay, and then by the way, let me make that. Can I make it a dotted line? I don't know if I can. Yeah, I can't. So just let's make this like a makeshift dotted line then. Oh wait, not that one. I'm so sorry, my friends. This one is the dotted line right here, isn't it? Yeah. So let's just see. This will be dotted, right? See how it's dotted? I'm trying to make it a dotted line. Use your imagination, guys. Okay. I think you could follow my point. But then, of course, this certainly is a solid line here. See the idea? And it goes on forever. And likewise, we also have, I think I can like spray in there. Maybe not. Yeah, I think I can. Okay, so let's see if we can color in here. Yeah, I can color in. Oh, fun. Okay, I'm coloring it in purple. See how I'm coloring it in? All right. So I hope that you guys are getting my little lesson here and the idea of what I'm doing here. So I'm trying to color it in. All right, so see what the solution is now? The solution is not the picture you're looking at. The solution is the very intersection of those two shapes. Try to imagine they're like two panes of glass, like a gray pane and a bright orange pane. And when they match together, they make that funny purple color. Also notice that in my solution graph, I'm very deliberate about where the dotted lines are and where the solid lines are. So what is the solution here? Remember, they're asking you for a graphical solution. So that's the answer, that picture. You don't have to write some kind of algebraic answer. That's the actual answer, the actual picture you're looking at. And notice that I carefully included dotted lines where the dotted lines were and the solid line where the solid line was. And we have our solution there. All right. Okay, now, for example, 3, we have a graphical solution of a system of equations, but this time we have actually a couple more constraints. And I want to focus with you on one particular specific part of this that's important. Take a look at what's written right here. That is a statement that all of the x values are positive and all the y values are positive. The easiest way to interpret that is stay in quadrant 1, where all of the points have positive coordinates for both x and y. When you see that, and that's a common thing that will appear often in your studies of linear programming, that last constraint that x and y must be positive. When you see that, basically just try to remember that you always will have the x and y axes as boundary lines right here. Let me use a different color. Here you go. So these are definitely going to be boundary lines for sure. Okay, and that's what that means. Now, if you want to include that in Desmos, when you type your syntax into Desmos, here's how you do it. You take the two inequalities that you see, these two, and you ignore the last one for a minute. You type them in, but then after you're done typing them in, you type this syntax in. Guys, look at this syntax right here. I want to try to make it so that, let me make it thinner. Can I make it thinner? Yes. Okay. There you go. That's better. Okay. See the little green box I'm making? I'm trying to show you that when you put in your, when you put them in to Desmos, you can include this. When you see that last constraint in the purple box, you can include what I've written in the green boxes right after. And notice that you don't put a comma or a semicolon or any kind of dash or anything. You just put in your inequality the way it is. X plus 2y is less than or equal to 10. And then you just type that in right there, and it will do the same thing. Now, you don't really necessarily even have to put that in. If you understand the concept of that you're only looking at the first quadrant, you can just put in the inequalities the way you see them and use your imagination to realize that, you have that red angle that I put there, and that's a constraint too. So I'd like to take a minute with this one and show you how to go in cold into Desmos and how to get the graph of it using this as our model. Let's do that, okay? So let me share Desmos with you. All right, we're in Desmos now. So now let's put the inequalities in. I'd like to show you first what they look like without the x greater than 0 stuff. And also, when you're putting your inequalities in, if you find yourself needing to use a less than equal or a greater than equal, you can access them down here in the keyboard. All right, and you see it's right here. Here's your function key. So the first one in the model was x plus 2y is less than or equal to 10. And it's all that. And then the next one here is 2x plus y is less than or equal to 14. And it's that one. Now, look at our graph here. If I know that I'd like to see the actual top points of it, so what I'll do is I'll zoom out a little bit with my zoom, and I basically have it now. I have it, and I can use these important places. See how I have the 10 zeros there, and I have the 6, 2 here. I can identify this top point 0, 14, and then I can identify this is 7, 0. So I could reconstruct this, or at least compare this to different answer choices in WebAssign and make sure they get the answer right. If I want now, I can also remove all of the stuff in the second, third, and fourth quadrants here that don't fit with the picture by including that syntax. So here's what I'll put in. I'll put in x is greater than 0. Oh, sorry. I have to put in a space and then the fancy brackets. Fancy brackets can be found above the enter key, right? X is greater than 0. Close, oh, not O, 0. Close, and y is greater than 0. And I could do that also here. In fact, if you want, you could copy and paste it and put it here. And now there's your picture. Maybe I'll drag it over here, zoom in on it, get a better picture of it. Zoom out once. There you go. And you can look at where they cross and all that good stuff. And remember that this, okay, this point right here and this point right here are not what's important. What's important are these points right here. This one. Oh, you can't really see that. Hold on. Make it black. This one. Wait a minute, why is it like that? Oh, I have the wrong thing. This is what I mean to do. This one. There you go. Okay. This one, and this one. So the solution is a funny quadrilateral. See the quadrilateral in there made by those 4 big black points I made? The reason why is because remember, when you're solving a system, you're trying to find intersection. And if the two things make triangles, they intersect to make this odd shape. The solution is not the blue or the red part. It's the area inside the funny quadrilateral with the 4 points I just made. Okay? All right, good. So I think that we all understand that, and I hope that that's really clear. It should be a cinch. Now you could go into WebDesign and go and do all your homework. That's basically the whole idea behind solving a system of inequalities. Now we're going to use this as an application to apply linear programming to application to business models. I'll show you how that works next, okay? So now that we're familiar with how that works, let's see if we could apply this now to an application. Now we're still not quite doing linear programming as of yet. We're just at the end of chapter 4.1, and this is an application of something like that, okay? I'll read out loud. I'm going to ask you to try to focus with me and follow it. It says CDF Appliances has assembly plants in Atlanta and Fort Worth, where the company produces a variety of kitchen appliances, including a 12-cup coffee maker and a cappuccino machine. The following table shows each factory's assembly capabilities for the two products and the numbers needed to fill the orders. And I have a table here. The table is talking about two different locations where I'm making my appliances, Atlanta and Fort Worth. It's also talking about the two kinds of appliances I'm making. I'm making coffee makers and cappuccino machines. We have some information about what it's like to make a coffee maker at Atlanta. We can make 160 of them per hour if we use the Atlanta factory. We can make 800 coffee makers per hour if we use the machinery in the factory at Fort Worth. Likewise can be said for the cappuccino machine in Atlanta and Fort Worth, respectively. It is crucial that for our market equilibrium and for our sales to be in the right place, that we have at least 6,400 coffee makers to put on the shelves in all of the stores. It also is crucial that we have at least 40,000 cappuccino machines. So look at this table. It's a lot of information and it's kind of complicated, but you don't have to really delve into all of this if you just understand that you can make statements with inequalities and observe what the graph looks like and use corner points, right? So the question says, write the system of inequalities that describes the number of assembly hours needed at each plant to fill the orders and graph the solution region for the system. So if we need at least 64,000 and we can make 160 per hour, we can make statements based on that idea. First of all, 160 times x plus 800 times y is greater than or equal to 64,000. What does that mean? That means that if I think about the number of coffee makers I would make in Atlanta and the number of coffee makers I would make in Fort Worth, I would be able to add them together and it would be at least 6,400. So that's what X and Y are representing in this case. And the same thing with the cappuccino machine. For the cappuccino machine, I have 200 X, which is the number of hours that I would be spending working on cappuccino machines, and then 200 times Y, which means 200 times the number of hours I would be working on cappuccino machines in Fort Worth, but it would be greater than or equal to 40,000. And we also have, of course, constraints because remember, X and Y can't be greater than 0. How is that, would that be possible? We can't have that. That doesn't make any sense. All right. So I'm going to pause here. I'm going to ask you to give this a shot, okay? Right now it's 9:25. We'll break until 9:35. See if you could solve the system that's given right there. It's an application of the ideas associated with the CDF appliances. We'll be back at 9:35 with the solution. Okay, so to get our answers, what we got to do is go into, what we have to do is go into Desmos. And when we go into Desmos, it looks a little bit like this. Oh, wait a second. When we go to Desmos, it looks a little something like this. Sorry about that, guys. Here we go. All right. And I took the liberty of going ahead and putting them in, and I know that you guys did that too. All right. And here they are. Now I can't see them, so I'm going to zoom out a little bit, see if I can get a little bit of a view of them. And there they are. Now, in this case, you'll notice because of the way that it turns out, notice it has greater than or equal to, and we have a strange situation where we're looking at an infinite unbound area, and it's not a polygon that was enclosed like the last one was a quadrilateral. Instead, it's going to be more along the lines of an unbound area. So it will have a point here, here, and here, right? And we're going to disregard all of the other stuff everywhere else. And the actual solution set will really actually be all of this and then to all of this, and then to this, and then to this. Okay, so I hope that that's clear, my friends. Does everybody understand? The purple part is the answer, right? And so the other parts are kind of the shaded pieces outside. And as you can see now, yes, sometimes you'll have an unbound area as your solution set for a graphical solution when you're doing a system of inequalities. All right, now, what are those points? Just for our own help, what are those points? I would kind of point in that area kind of and hover there to get it. Let me get rid of my drawings. And I can do that now. So that's funny, it's not letting me get them. Usually it does let you get them. There we go. Well, for something like this, you'd probably have to just zoom in and look very closely. You could see it's 150, 50 there. Out here it's 400, 0. Over here it's 0, 200. I think it's because of the view or because I'm sharing that it won't let me do it or something like that. But anyway, I hope that that's clear. That's how you would get them. All right. All right, let's go back to our PowerPoint and let's now think about chapter 4.2. In 4.2, it's going to be the same thing you just did, except there's going to be a little bit of an extra thing to do when you're done with that. So first you'll get a system of inequalities like you see on the left. You'll go through the work we just did and you'll make a nice graph out of it. Then after you have that graph, then you'll have what's called an objective function. I'm going to read this out loud and then we'll discuss all the ideas here. The basics of linear programming. Given an objective function f of x, y, and several constraints, first graph all the constraints. What are constraints? It's everything you see in the system. These are the constraints. There are 3 of them. Okay. And then it says observe all the corner points, which I showed you how to do. We could do that and get what all the corner points ought to be. Then find f of x, y. And I'm going to show you what that means in a minute on paper. All right. Last, select the f value that represents the max or the min. And also note that depending on the image, it should be clear if there is a max or a min. In the last picture, there was an unbound area that went upward. That means there's no max. And sometimes in the same way, you can have a shaded area that goes downwards in some direction. You could say there's no min. So it's going to be a matter of graphing the inequality, observing those corner points, and then taking each of those corner points and carefully substituting them into the objective function f. And then for each of those answers, you'd select the number that is the lowest or the number that is the highest, based on if you're trying to find the min or max, respectively, and then you have your solution. I want to show you a little bit about how that works with the function capital F. Okay, friends, if you're looking at this and you see the whole picture, that's good. But if you don't see the whole picture, go into the top right and click View and change your view from gallery view to speaker view in Zoom, and you'll be able to see this very clearly. Okay, so I'd like to show you now how to use an objective function and what it means to determine max or min. All right, so let's make up a function. In fact, let's use this function. F of xy equals 3x plus y. Okay, this is my objective function. And let's pretend that you went in with a system of inequalities and you carefully graphed that system, and then you got a beautiful image in Desmos, and then you were able to observe all the corner points, and then you had those corner points as 1, -6, 3, 5, and 0, 7, and 2, 0. All right, because remember, there's going to be 4 points, or maybe there will be 3, or sometimes you'll see even 5 or more. But in other words, all the corner points of the intersection polygon or unbound area that is made by the system. Now, here are 4 points. Every point has an x value and then a y value, So for this one, to find f of this, it would be 3 times 1 plus -6, which is -3. For this one, it would be 3 times 3 plus 5, which is 14. Here, and I forgot to f, so finding f of these, So this one is 3 times 0 plus 7, which is 7. And this one is going to be 3 times 2, plus 0. Okay, so notice that for each of these corner points, I was able to substitute the x and y values into the objective function, and it gave me solutions. If I said which of these points maximizes the objective function, it would of course be the 0.35 because 14 is the largest. If I said which of these would minimize, of course it would be 1, -6 because that's the lowest. And that's the whole story, guys, of what linear programming is. It's a matter of graphing the inequalities like we learned on, and then finding the intersection of the polygons or the areas. And then looking at those actual corner points. Remember when we were looking here and we had corner points? We would take corner points like 0, 200 and 150, 50 and 400, 0 to get that. And after we did that, we put them into something like this. Okay. All right. So all right, friends. So now here we have a case where we're graphing three different we have three different constraints, and we have an objective function f. You can call it capital F, or you can call it capital F of x comma y, but anyway, there's the objective function, and we're asking you now to figure out whether it's maximized or minimized, And here we have the graph that we would get if we put all of that together in Desmos, and we can identify what the points would be. And we've done that application a couple times, so now you know how to do that. There's a system. That's what the graph looks like, okay? And if you look at the points, observe the corner points. One of them is 0, 10. One of them is 10, 8. And one of them is 14, 0. So what we do next is we figure out first we figure out, are we maximizing or minimizing? Look at the actual question. Example 1 says maximize. Maximize the objective function, and we give f equals 3x plus y. As you see, I used that for our example when I was explaining the objective function. And here we have three constraints. So you would go right into Desmos and graph it and get these points. We have 0, 10, and 10, 8, and 14, 0. So look now at the arithmetic associated. We figure out for 0, 10 what it would be, and look, I worked it all out to show you. We do it for 10, 8, I worked it all out, and we do it for 14, 0, and I worked it all out. Which of these has the maximum? The biggest number there between 10, 38, and 42. The biggest number is 42. So it then becomes clear that it's the point 14, 0 that will maximize the objective function at 42. The wording looks like this. The maximum value is 42 at 14 and 0. All right, so it's just a little bit more than we've already learned. And as you can see, it's really not that hard. It's just a little bit of function stuff that you might remember from your algebra classes back in high school. Now let's try another one. This one is an application. This one is about a farm. I'm going to work through all of this, and then we'll set up some constraints, and then we'll look at an objective function. We'll create an objective function, and we'll try to set up a way to go about answering this question using all of those mechanics we just described, including using a function in two variables and graphing inequalities and so on. The question reads, a farm co-op has 6,000 acres available on which to plant corn and soybeans. The following table summarizes each crop's requirements for fertilizer and herbicide, harvesting labor hours, and available amounts of these resources. So let's try to examine the table for a minute, try to grasp the table. And I encourage my students, whenever you have a word problem that has a table in it, I need you to look at the table before you dare to answer the questions and make sense of the table. Like you could just try to read the question and then go right to the table and try to figure it out. Or you could look at the table and say, what is the table telling me? That way I can navigate through the table quickly and easily when I do know what it is I need to figure out. So what is this table saying? Let's see. It says that when it comes to fertilizer and herbicide, I need 9 gallons per acre of corn that I'm planting. And I also need 3 gallons per acre of soybeans that I'm planting. That's how many gallons of fertilizer herbicide I need for corn and for soybeans per acre. And by the way, in my shed, I have 40,500 gallons of the stuff. Okay. Next, harvesting labor. For harvesting labor, when I have people working for me, It'll take them about 3/4 of an hour to harvest 1 acre of corn. It'll take them 1 hour to harvest 1 acre of soybeans. Don't let that fraction scare you. It's just 0.75. No, don't let it bother you. You know, we can put it right into Desmos. Desmos will handle it, okay? Last but not least, what does that figure 2520 mean? I'm sorry, 5250. Whoa, excuse me, 5250. What does that mean? Well, 5250 is the number of hours I have available, meaning I have X number of employees and Y number of hours per week that I have just 5,250 hours to spend amongst this work and to organize my employees to carry out all of the work associated with the fertilizer, the herbicide, and all of that. Okay. So some things that I can see looking at this, if I make X the number of acres of corn and Y the number of acres of soybeans, then I could say there's 9X and 3Y and is associated with 40,500, you know. And the same thing with 3/4 X plus 1/4 Y ought to be, I'm sorry, plus 1Y, right? Ought to be 5250. Let's look at the question now. It says, if the co-op's profits per acre are $240 for corn and $160 for soybeans, how many acres of each crop should the co-op plant to maximize the profit? And what is the profit? That's a deep question, right? How are we going to answer that? Let's take a look. Starting with, we do believe that X plus Y is 6,000, is less than or equal to 6,000. Why do we believe that? Well, remember, X is the number of acres for corn. Y is the number of acres for soybeans. And we are told that the co-op has 6,000 acres available. So in theory, you really could plant any number of acres up to, but including 6,000. Could I plant 6,001 acres? No. My farm is only 6,000 acres large. Okay? So X plus Y will be less than or equal to 6,000. That's your first constraint. The second constraint is that if X is the number of acres for corn and Y is the number of acres for soybeans, then 9X plus 3Y has to be less than or equal to 40,500 because I only have so much fertilizer herbicide in the shed. Next, when it comes to labor, I can have as much as 5,250 hours of labor to happen with my group of employees for one given week. I might not need that much. I might need only 5,000 for, you know, whatever my reasoning is. But the point is, I cannot exceed 5250 unless I pay overtime, and nobody wants to work overtime. You know, that's the case. So if it takes 3/4 hours for the employees to work on 1 acre of corn and 1 hour for the employees to work on 1 acre of soybeans, then I have a new constraint that 3/4 X plus 1Y must be less than or equal to 5250. And notice that all of the symbols are less than or equal to in this case. The reason why they're all less than or equal to is because you have a limited amount of resources, and this has to do with the resources associated with operating a business. Now you can apply this model of the farm with the acres and the hours and all that stuff to a lot of different kinds of business models. You could do this for a video game that has for video games being made that have microchips and plastic in them in 2 different locations, or with 2 different kinds of things going on with them. You can really apply this model over and over again to all different kinds of business things. And ultimately, what it really boils down to, my friends, is having a solid grasp on your business to the point that you really do understand what the constraints of your business are. You just cannot plant more than 6,000 acres. That's it. You just don't have more than 5,250 hours of labor available amongst your employees. That's it. And those limits are what kind of make you think, well, how many acres of corn should I plant? And how many acres of soybean should I plant? Since everything is so different, there's probably an answer that represents the best I could do. And don't you want to maximize your profit as a business person? And that is the whole angle here, okay? So we read the question carefully and we try to come across how to write out a list of constraints. In this particular case, by the way, this is a more advanced one. You'll notice there are 4 constraints here. Up till now, we've only done 3 constraints. Here we have 4. So we have to take all of them into account. And the good news is we don't have to really do any math or arithmetic. We just have to understand the concept and be able to use technology now to try to figure out those objective points. All right. So what we'll do is we'll take this right here and we will put it into a system and we'll go and graph it. When you graph it, you'll get an image something like this. As you can see, the axes are very far apart, so you'll need to zoom out when you do Desmos. And further, all of the points are actually given for you here. You'll see, and I'll highlight them for you now. Here's the first one. Here's one. Here's one. And here's one. And by the way, your profit is the objective function. And the profit came along with how much it costs for the soybeans, how much money you'd make on the corn, and how much money you make on the soybeans. They told you per acre you expect to make $240 per acre of the corn and 160 per acre of the soybeans. And that's why P equals that in that way. So now what you'll do is you'll take each of those points and carefully plug them into the objective formula like you see there to see which of them gives you the maximum amount of money so that you can make the most money and the maximum profit. Something like this. Just like I showed you earlier, you take the function, you put the points in that you found as the corner points there, and you figure out which one has the largest amount. And welcome to quantitative analysis, where your business actually earns millions of dollars. So it is kind of practical here that if you look, we have very large amounts, and this is the very largest amount. What does that actually really mean? That means if you want to make the most money in this situation with this kind of farm, with this many gallons of fertilizer and herbicide, and with this many employees' hours, where the profit happens to be 240 for one product and 160 for another crop, the answer is please plant 3,750 acres of corn and 2,250 acres of soybeans. That will give you the maximum profit. And look, it's a pretty big change, don't you think? You know, 1,260,000, that's a lot more than 840,000 or 12 or 1.2 million. As you see, that 60,000 is a very large differential. It makes a very big impact when you have a large farm like this. So it is kind of important to know how much to plant of what. Knowing that will maximize your profit. That's the point of the whole lesson. All right. Linear programming has to do with using constraints to be able to get the best or the least. Okay, so now for this one, you'll see an example now where you wind up with a unbound area. And the good news is we're asking for maximum and minimum here. So you're going to see a situation where you have to use your own intuition to interpret the graph to realize that you cannot have one of them, that a minimum is not possible or a maximum is not possible. I'm going to let you give it a whirl. You try it on your own, please. Here's everything you need. There is a very basic very basic objective function. It's right here. They're calling it C because it has to do with cost this time or something. And then you have three constraints. They're right here. I'll give you 10 minutes. See if you can figure it out. And when you're done, we'll get together and I'll show you the solution. Okay, it's 9:55, 10:05, we'll return. Welcome back, students. So let's go ahead and go through this now. We have a cost function given here, and this is going to be our objective function. It's just x plus y, but it is just very easy to simplify, to substitute right in there the x and the y. Don't let that throw you. Sometimes when they make it very easy, students get confused. It is just add them up, you know, and here are the three constraints. So what I did was I went into Desmos and I entered those constraints in. Here are the here are the images. Okay. And I had to move around a little bit. I'll show you what I mean. If you click home, you're here. And I kind of can't see what's out there on the far right. But if I move you know, you can click and drag and move it around any way you want. So I'm going to move it like this so I can get a good image. And it's not showing me the actual point when I point to it. I think that's because I'm in Desmos with you. I mean, rather, I'm in Zoom with you. But you should be able to get those points pretty easy. And here you could see the point is 0,6. Here you could see the point is 2,3 if you look closely enough. And you'll notice that here the point is 11 comma 0. And remember, my friends, I do need you to think about this point, and this point, and to ignore the blue and orange pink triangles you see there. The actual solution graph looks like this. Oh no. It's this, and then this, and then this here, and then this. Okay. So we have points there. The points look like this. Points are 6, 0. No, 06. What am I saying? 06. Hello. All right. Here we have 2 comma 3. And here we have 11, 0. So those 3 points are the points that we're going to test the constraint with. Now, we're asked to find out what is the minimum and what is the maximum. Before we go in using the function and using algebra to get numbers, we have to observe the graph and use a little of our own critical reasoning, critical thinking skills, all right? You see how the purple image, we know that that is ultimately going to be an unbound area, and it's unbound in this particular direction, right? Doesn't it go back, doesn't it go up forever and ever this way, right? Okay, so doesn't that mean that there's no maximum? It does. It means there's no maximum, and it's important you know that looking at the picture before you start doing the algebra, because when you do the function with these 3 green points I've written in here, you will get a smallest number and you will get a biggest number. The biggest number, however, is not the maximum because of the way this image is, it's unbound. So sometimes there isn't a max, and you can only notice that after you've carefully graphed the 2 inequalities and noticed their intersection with linear programming this way. Okay, so that's something else that is a little bit of a curveball in linear programming. Just keep your eye out for sometimes that you don't get a polygon. Like this is not a polygon. This is an unbound region, which is not a polygon. All right, now we'll leave all that stuff right there. I'm going to use 0, 6, 2, 3, and 11, 0 and figure out the objective function. So take a look now at what I have here. And I've written my objective function here for us. And now I'm going to test each of these points and see, which one is the lowest. I don't care which one is the highest because I already determined that there is no max. Okay, and I've already determined that by looking at the graph. I'm looking for a min right now. All right, so this is an x value and this is a y value, plug them in. It's easy this time because it's just x plus y, so it's just 0 plus 6. This one is just 2 plus 3. You're back in kindergarten. You're 11 plus 0. Which of these is the smallest? So you can minimize the cost if you use x equals 2 and y equals 3. That's your answer. Okay. So just to review, go into Desmos and enter the constraints. You get an image kind of like this. Notice that it's unbound up and to the right, which means there's no max. And then take those 3 points and use the objective function to put in those values and find out which one is the minimum. And there's an airplane outside. Sorry about that. I also have a fire engine down the street. You might hear them. That's a pretty loud siren that goes off once in a blue moon. Anyway, please excuse the airplane going overhead. I live in Galloway, very close. I live in Egg Harbor City, very close to the Atlantic City Airport. Anyway, so as you can see, we're going to say the minimum value of C, of course, is 5 because of the 0.23, and the maximum value does not exist. There is no max because we have an unbound region. Okay, so that's all I got for you guys. I don't want to keep on preaching and barking at you. This was a short lesson, but as you can see, it's a pretty thick lesson. There's a lot of great stuff in it, and I will ask that you now go into WebAssign and try to get those questions done. They're very closely associated with this skill set. I hope you enjoyed our lesson about linear programming. And now when someone says linear programming, most people will cringe and say, oh, that sounds horrible. And you can say, oh, that's a piece of cake. I know how linear programming works. because I have Desmos, and because I have a great teacher, Mr. Marquetta. Anyway, enough about me. I hope you guys have a great day. It's 10 after 10. And thank you so much for listening to my lesson and for paying close attention to all of my images I created for you. We're going to stop the film now, and I'm going to go ahead and open the floor to questions. Thanks for your attention, guys, and have a great day.